So the first thing I'm probably going to do is think about rewriting this first term on the left-hand side. If I multiply both the numerator and denominator by a factor of x, the numerator is going to become 2x squared, and the denominator is just going to become the number 1, right? X to the negative 1 times x to the first, minus an x, and then plus the number 48. So that's my right hand side. On the left hand side, there is a binomial here. I've got 2x plus 1 times x minus 4. Not entirely necessary, but I'm just going to draw a quick area model. I've got a 2x plus a 1, and I'm multiplying that by x and negative 4. When I put the pieces together in that upper left box, that's 2x squared. And then I've got an x, and then I've got negative 8x. That's the 2x times negative 4. And then I have negative 4. These two I can combine. Negative 8x and x is just 7x. So I can rewrite that first part of the equation using the information in the area model. 2x plus 1 times x minus 4 is the same as 2x squared minus 7x minus 4, and then I'll write over here plus 10. Of course, these two together make a 6. And the other thing that's true is both sides have factors of 2x squared. So I'm going to subtract the 2x squared from both sides and combine the negative 4 and the 10. It's going to give me negative 7x plus 6 equals negative x plus 48. If I add an x to each side, I'm looking at negative 6x. That one just got a plus x. Whoa. And then plus 6 on this side. And that's going to equal a 48. Take away 8, or take away 6 from both sides, rather. It's going to become negative 6x equals positive 42. And by the division property of equality, x would have to equal the number negative 7. So this is my value of x. If I plug it into the original equation, I could verify that it does indeed make the left and the right hand side the same number, which is super cool because that's what a solution is. Let's go to E. E is a lot like the one right above it. The difference is with E is that, yeah, I could think about looking inside, but the problem is I don't know exactly what that has to be. So I want to get to a point where I have that square root part of the equation by itself, and I can more easily identify exactly what the 2x plus 1 has to be by looking inside. So I'm going to subtract 5 from both sides. This is going to become 3 times the square root of 2x plus 1. And if I take away 5 from 32, that gives me the number 27. And then if I divide both sides by 3, I get the square root of 2x plus 1 must be the number 9. And it's the same thing it had to be above, isn't it? This thing inside must be the number 81. So I can write that value, that 2x plus 1 must be the number 81. Therefore 2x must be 80, and half of 80, this time x is 40. Above it was 20. So x has to be 40. A, B, C, D, E. Let's jump over to F. On F, I can see that a quick multiplication of both sides by the number 10 would eliminate these fractions entirely. So I'm going to multiply both sides by 5 times 2. When I hit the very first term, by the way, yes, there are 4 terms. This is a term, that's a term, that's a term, that's a term. And I'm multiplying by 5 times 2 in each one of the numerators, to be clear. When I hit that first fraction by 5 times 2, the 5 in the denominator with the 5 that I'm multiplying it by are gone, and I just have to multiply the 3x plus 2, that entire numerator. I have to multiply it by this 2. So it's going to become 2 times 3x plus 2 plus the next one. You can see there's a giant 2 in the form of, there's a giant 1, a giant 2. It's a giant 1 in the form of 2 in the denominator, 2 in the numerator. So that's just going to give me 5x plus 5x. That's going to equal So the 5 times 2 is just 10, so this is going to be a 10x. 5 times 2 is 10, so 10 times 5 is plus the number 50. If I distribute here, this is 6 times x plus 4 plus 5x, and that's still 10x plus 50. Combining my like terms, this is 11x plus 4 is 10x plus 50. Taking away 10x from both sides, I just have an x over there now. So x plus 4 is the number 50. And when I take away 4 from both sides, I get that x has to be the number 46. So the final problem on that page was, nope, there's one more on this page. There's G. So x is 46 for part F. This is the final problem. Ooh, okay. So before we saw, what was it, 1/5 and 25. When I look at this, I can actually think about this as fours, right? Or I can go back to the fact that these are also factors of 2. But it's kind of a unique situation here because 4 is 2 times 2, and 16 is 2 times 2 times 2 times 2. So I can either go to a common base of 4 or a common base of 2. I think the 4 would be easier, so I'll use that. So I'll just write as a reminder myself, 4 to the 0 is 1, 4 to the first is 4, and 4 squared is 16. Going the other way and dividing by 4, 16 divided by 4 is 4, 4 divided by 4 is 1, 1 divided by 4 is 1/4, and that's what 4 to the negative 1 is. So those are the two that I want to use, right? I'm going to use this as a replacement for 1/4, and I'm going to use this as a replacement for 16. So I can rewrite the equation as 4 to the negative first power, and I'm going to raise that to the 3x plus 1. And on the other side, that's going to be 16 I'm going to replace with 4 squared, so it's going to be 4 squared, and that's being raised to the x minus 2 power. Again, I'm raising a power to a power, so I'm going to multiply this negative 1 times the 3x plus 1. I should say times the quantity 3x plus 1. It might be helpful for you to put parentheses here to remind you that that negative 1 has to be multiplied by each of those two terms. And I'm also going to multiply this 2 times this x minus 2, each of the terms. So I can rewrite this as 4 raised to the negative 3x minus 1 power, and that's going to equal 4 to the 2x minus 4 power. I now have exactly the same base, so looking inside I can assert, well, this exponent, right, 3x minus 1 must be the same as this exponent. They must be the same. I'll take away, let's see, which way should I go? I'll add 3x to both sides. So this is going to become 5x minus 4. And now I'll add 4 to both sides. So this is going to become negative 1 and 4 is going to be a 3. Negative 1 plus 4 is 3 equals 5x. Therefore, x is going to be 3/5, right? I'm going to divide both sides of that by 5. So x will equal 3/5. And there we go. I think that is that's it for page 3. Let's move on to page 2. So on page 4, we have a couple 4 rigid transformations, and let me read what it says here. Polygons that undergo a rigid transformation do not change in shape or size. So they're definitely going to move somewhere else, and their orientation can be changed, but they're going to be the exact same shape and the same size. Carefully subject each polygon to the indicated transformation to produce an image of the original object. Label point A prime and find its coordinates. So the only coordinates I want you to write down are the ones that happen with A, but I want to see the transformation also. So several of you have been talking to me during office hours, and you've expressed an interest for developing rules to make this a more straightforward process. Some of you have used some wax paper or some of the patty paper in the classroom. During the test, if you find a piece of the patty paper helpful, I would be happy to let you use a piece of it. But for 180 degrees clockwise rotation, in my mind, I know the entire shape is being, rotated around the origin here. So I'm going this direction around the origin. And basically, this is kind of the leading edge. So when I go 90 degrees, that leading edge is going to be somewhere over in here. And when I go the 180 degrees, the leading edge is going to be, it's going to be somewhere. Gosh, this is always probably more difficult than it probably should be. Let's take a look at the transformation rule. Actually, let me do this instead. So this is actually just me thinking live and just thinking about a way that I could tackle this. I do know that if I was to look at this line segment and I rotated it through 90 degrees, I don't think this dotted line has anything to do with that, but if I went through 90 degrees, right now it's down 2 and then over 1. I know that it's going to have to be up 1 over 2. So this point is going to go to there, right? So that point is going to get located at this spot. Now that's just after a 90-degree rotation. And if I track that point, this point was at -1, 2, and then it's going to go to 2, 1. So you can see what happens. What was y became x. So you can see y was 2, and that became my x value, which is 2. And what was x, the opposite of that, became y. Now, the same thing's going to be true if I go another 90 degrees the other way. If I do that, continuing on 90 degrees, I'm going to end up at this point right here. And if I think about the coordinates of this point, x is going to be the number 1 again, and y is now going to be -2. Now, that's a cool observation, right? So it's my theory that if I have an xy point and I rotate 180 degrees about the origin, what happens is xy stay in the same location, but the new x is going to be the opposite of the old x, and the new y is going to be the opposite of the old y. So I can write this down as a rule for 180 degree clockwise rotation, right? And xy is going to simply become the opposite of what x was, comma, the opposite of y. So that is what I'm going to use to figure out where the heck this thing goes. Now I just did that point that I did it for is the a prime. So I believe that's where a prime goes. Let's try the rest of it and see if that works. Okay, so I'm just thinking about that rule and seeing if I believe it or not. So this point right here, this point was x is -1 and y is 3. So what I'm going to do is I'm going to keep x and y the same. It's just I'm going to go to +1 and then -3. So that should be this point. So it looks like I've got one of the sides here. Now I think, right, I think I see what's happening. I think this is going to be the next point here, and I think this is going to be the next point. But let me check and see if my rule's still working. So this point right here is at 2, x is 2, y is -2. Over here it was -2, +2, -2, comma, +2. So what I'm saying is x and y stay in the same spot. I just flip it. X was -2, it becomes +2, check, and y becomes -2. That's exactly what's happening. For this point right here, x was -3 and y was +3. So for right here, x became +3 and y became -3. That's fabulous. And then the very last one, this is -2, 0, so it's going to become +2, and 0, the opposite of 0 is still 0. So this is where this shape goes. So this is a 180 degree rotation about the origin. 180 degrees. Okay. So not content to leave that alone, I decided to go ahead and throw that into Geogebra, and I created a slider here so that I can rotate through 180 degrees. And if you'll notice, they both start at the point x is -1, y is 2. And when I go through to 90 degrees, let me hit 90, it's right there. So when I go through 90 degrees, it's exactly what I saw with thinking about just those 2 points that connected from the origin to A and from the origin to the A prime. X and Y switched places, except for Y became the opposite of what X was. And then when I go through another 90 degrees and land at 180, you can see what happens here is, yes, X and Y are in the same location now, but instead of X I have the opposite of X, so -1 became +1, and instead of 2 I had -2, so Y became the opposite of what Y was. So if you're interested in a transformation rule that rotates something 180 degrees around the origin, that's it. And that's okay if that's where we want to keep our thinking right now, but not knowing and being able to come up with a rule like that, that's kind of that's the bigger goal, right? To be able to think through something like that. So let's go ahead and look at this next one. And this kind of thinking gets us actually pretty far with this. What we want to do is we want to reflect across the line y is equal to x. And what's nice about that is that rule right there, reflecting across that line, really gives me my transformation rule. So what was xy? If y equals x, then that means that what is x will become y, and what is y will become x. And there's no sign change, so this is different than the rotation, the reflection. So let's go ahead and take a look at what happens to these points. So if I think first of all about just the point A, x and y are just going to switch places and keep the same signs. So I was at -2, 2, so it's going to become 2, -2. So 2, -2 is going to become my A prime. That's the point that I was asked to track. It's at 2, -2. The point off to the side there, this point is -1, 2. So that's going to become 2, -1. So, no, I have to flip them. This is -2, 2. So it's going to become -1, 2. No, wait a minute. Let me think about this. I think what I need to do is, yeah, that rule's helpful, but I should just write down this point. This is the point -1, 2. So what's going to happen now is I'm going to go x is 2 and y is -1. So this is going to be that point. And then I've got this point here. Yeah, writing these numbers down helps me. -1, 3. So now I'm going to go x is 3, y is -1. Okay. And then over here, I've got this point where x is -3 and y is 3. So now I'm going to go to the point 3, -3. So 3, -3. Okay, I definitely think I see the shape emerging here, right? I've got this, this, this. This point right here, this is the point -3, 0. So I'm going to go instead to 0, -3. So that's going to be this point. And at that point, I think I've got all of the points and I can go ahead and sketch it. So this is the reflection across the line y is equal to x. The other way I can get it kind of just visually is just by, if I look at this, right, this is like 1.5 diagonal to the line, a half, and then another 1 diagonal to the line. So I can draw these lines like this, like that's 1, 2 diagonals, 1, 2 diagonals, 1.5 diagonal, 1.5, or a half and a 1 diagonal. That's nice. This one's like, this is 1, 2, 3. No, it's 1, 2, and then 1, 2 diagonals. Yeah. So this is the reflection across the line x equals 1, and I result in this. And if you're interested in thinking about these, right, I don't tend to memorize these, but you can see it takes me longer to think through what they are. But that's a rule for reflecting across the line. Y is equal to x. Let's go down to C. Oh, C looks like it's easy. It's easier because I'm just reflecting across the x-axis. So I'll do that in this purple color. So to reflect across the x-axis, right, I'm just like, this is 1 away, so this is going to be 1 away. And then this is 1 away, so this is going to be 1 away. This is 2 away, so I'm going to go 1, 2, 2 away, 1, 2, and then 3 away. So there I go. So this is the shape after that reflection. I find it's super easy to reflect across the x-axis and the y-axis. I don't think there's and there is a rule for it too, right? If you've got x, y, and you want to reflect across the x-axis, what happens is x stays exactly the same, but the y's just become the opposite of what they were. So that is the reflection across the x-axis. This point A, right? You were supposed to list the coordinates of the new A prime, so I should write here that A prime right there is going to go to the point -2, -2, and before it was at -2, 2. So you can see that what I literally did was exactly what we said, right? We just took the opposite of the y value. All right, and then finally we're going to do a translation. It is a translation is a transformation. This is where it doesn't rotate, doesn't reflect. We're just going to slide it around. And this says that x's are going to increase by 5 units. So from my point A, I'm just going to go, it's increasing by 5. I'm just going to go 1, 2, 3, 4, 5. And then y's are going to decrease by 4. So I'm just going to go down 1, 2, 3, 4. This right here is my new A prime. This new A prime is located at 4, -3, and this shape would be pretty easy for me to draw. I'm just looking at the shape above. I got this diagonal, and then this. So this is that shape after that wonderful transformation. Okay, for sure, I don't think these are trivial. I think it takes quite a bit of visual perception, visual thinking to come up with these transformations. But that is question 4. Let's go down to question 5. On 5, I give you 2 function rules. I give you the rule G and I give you the rule F, and then I ask you to evaluate using some combination of those. In A, I'm simply asking what's G of 3, so that just means I'm going to take the rule for G, which is 3 times the input plus 5. The input is 3, so I'll place a 3 there. 3 times 3 is 9, and 9 plus 5 is 14, so we'll get the number 14 there. On the next one, we are asked to, this one looks a little bit more complicated. We're going to have to do both F and G, and we're going to have to add them together. Let's do the G first because that's pretty straightforward. So again, G is 3 times the input for G plus 5. Well, 3 times 2 is 6 plus 5 is, this part is going to equal 11. And then let's see if we can figure out what the F part of this is. So our input here is going to be -4. -4 is going into the function. So it's going to look like -4 over 2 plus -4 is going to be squared minus 5. -4 over 2 is -2 plus -4 times -4 is 16, and then a minus 5. So we've got 16 minus 5 is 11, and then 11 and -2 would be a positive 9. So I think I get the number 9 here. And if I combine those two things, I think I get 20. Let me double check here. Yeah, I'm definitely happy with f of -4 being positive 9. And 3 times 2 is 6. 6 and 5 is 11. So yeah, I've got 9 plus 11, which is 20. And then finally, we're asked to evaluate the function f when it receives the value of 2. I'm still thinking about this problem. 9 plus 11 is 20. So if I plug 2 into the function f, that's going to become 2 over 2 plus 2 is going to get squared and then minus 5. 2 over 2 is 1, so this is going to be 1 plus 4, right? 2 times 2 is 4. And then minus 5. Oh, guess what? We've got 5 minus 5. So when I put 2 into that function, I got that it produced an output of 0. So my answer for questions 5 are A was 14, B is 20, and C is 0. All right, next page, question 6. In 6, we're asked to find the equation line that goes through the points -10, 30, and 8, -6. Of course, I don't know what the slope is, so let's go ahead and find the slope. I'll remind myself I'm going to look at the change in y's, and then I'll figure out the change in x. So for my change in y, I'm going to say I've got 30 minus a -6, which is a 36. And then for my change in x, I'll single underline the x's, and I'm going to go the same order, so I'm going to just say -10 minus 8. So I'm looking at -18. 36 divided by 18 is 2, but 18 was negative, so it's the slope that I have here is equal to -2. So down 2 to the right 1. Let's figure out our y-intercept, and I guess I'll do that using this first point. All right, y equals mx plus b. Y, which is 30, equals my slope of -2 times my x value of -10, and then plus b. This is positive 20, so 30 equals 20 plus b, and that means that b has to be the number 10. So my equation should be y is equal to -2x plus 10, and it is very, very straightforward to check this. When I plug the number -10 in there, I get -2 times -10 is positive 20, and then 20 plus 10 is 30. And if I plug 8 in there, I get -2 times 8 is -16, and -16 plus 10 is indeed -6. So both of those check quite nicely. Next equation says find the equation line that goes through this point and is perpendicular to this line. So this was also something that we saw in Delta Math recently. I need to know the slope of this line, because if I'm going to be perpendicular to it, I know what to do with that, but I have to know the slope first. So I'm going to add 5x to both sides. So 3y equals 5x plus 12. And then I'm going to divide everything by 3. So y is equal to 5/3 x plus 4. So it looks like I have a slope here of 5/3. So if I want a slope that's perpendicular to that, the slope I've got to use is -3/5. All right. So make sure you understand that. I found the slope of the line, and this line that I'm going to draw now would make a perfect right angle with the line that I had. And I need to figure out the y-intercept, of course, but I've got an x value and a y value over here, so that's how I'll find that. I'm going to write y, which is 8, equals m, my slope of -3/5, times x, and then plus b. If I multiply those values, let's see, 15 divided by 5 is 3, times a -3 is -9 plus b, and that's what 8 is. And if I add 9 to both sides, I get that my y-intercept b would have to be 17. So my equation should be y is equal to -3/5 times x plus 17. And as a check, I'm just like saying, hey, are these the slopes of lines that are perpendicular to each other? And the answer is yes. And the other thing is, if I plug 15 into that equation, does it give me an answer of 8? Well, 15 divided by 5 is 3. 3 times -3 is -9. And -9 and 17 is indeed 8. So it works flawlessly. Next, I have three relationships here, and I'm asked to carefully and accurately graph them. The first one I'm going to graph is the last one. It's y is c. And, you know, it's like I can just plot a few points, or y is 5 rather. So all of these points that I'm plotting have different x values, but you'll notice the y is always equal to 5. So that's my first line. Grab my ruler, just set it to 0 degrees. Oh, come on, really? Put it right there. And there is my first line that I'll draw. Probably I should put little arrows on the left and right because it does continue forever. So this is my answer to C, which is the line y is 5. Now let's do B because that's nice. I know the y-intercept and the slope. The y-intercept occurs at -2, so I can place a nice dot there at -2. And then I can go up 3 units, up 1, 2, 3, and then over 1, 2, 3, 4, and 5. And I can go up 3 units, up 1, 2, 3, 1, 2, 3, 4, and 5. Just made that last one. So let's set this ruler so that the slope, it looks like it's the same, and I'll just pull that line through there. It's a good approximation. So this is the answer to part B, and this is the line y is equal to 3/5 x minus 2. The final one, don't know the y-intercept and I don't know the slope because that's written in standard form. So I'm going to add 2x to both sides. That'll give me 3y equals 2x plus 12. And then I'm going to divide both sides by 3. So I get y is equal to 2/3 x plus 4. Right? 3 divided by, or 12 divided by 3 is 4, and 2 divided by 3 is 2/3. So I have a nice y-intercept. It lives right here at 4, and I'm going to go up 2 units and over 1, 2, and 3. And I'll do it again, up 1, 2 units and over 1, 2, and 3. So I got 3 solid points, definitely a different slope from the line below, so let me adjust that. These lines will intersect with each other eventually. They're not parallel, right? So somewhere off to the left, I'm going to expect my last line and this line to meet. You can see they're getting closer to each other. This is my answer for part A, and it is the equation -2x plus 3y equals 12. And you can see I did rewrite that in slope-intercept form. All right, question number 9, last page of the test. It says express the area of the rectangle below as both a product of its dimensions and as the sum of the parts. The sum of the parts is the easiest one for me. So if I look at this, I can see there's 3x squareds, right? 1, 2, 3x squared. So I can write this contains 3x squares, and it contains 1, 2, 3, 4x tiles, so plus 4x. And then it contains just the number 1 by itself, so I hit plus 1. So in terms of its length and width, this dimension, right, that square has an area of x squared, so each side has to be x. This dimension has to be x also, and this dimension has to be 1. This has to be x long, this is x long, and then this is 1. So if I look at the dimensions, this is simply an x plus 1. That's the, I'll call that the length. And then this width, you can see I've got 1, 2, 3 x's. So I'll write 3x and then plus a 1. So I've got x plus 1 times 3x plus 1. And when I multiply that length and that width, I get 3x squared plus 4x and then plus 1. Question 10. I can see that this is a generic area model already set up. I'm multiplying 2x minus 5 times 3x squared plus 2x plus 4. If I were to fill in these parts, this is 2x long times 3x squared. That would give me 6 times x to the third power. Right? 2 times 3 is 6, x to the third. This should be -5 times that 3x squared, so this should be -15x squared. Over here I've got 2x and 2x, which is 4x squared. This is a -5 times a 2x, which is a -10 x. This is a 4 times a 2x, which is an 8x. This is a 4 times a negative 5, which is negative 20. So I can see all the parts. These are like terms, so I'm going to definitely combine the like terms. And I will write my sum of the parts here as, this would be 6x cubed. And then I would have minus 11, right, because I've got a positive 4x squared and a negative 15x squared. So I've got negative 11x squared. And then when I combine 8x and negative 10x, that should be a negative 2x. And then the last part is there is that negative 20. All right, now the last question. Same exact thing. There's a fairly large generic area model. I'm multiplying a times b times 3. Right? That's along this side, this one. And I'm multiplying that by a plus 3b minus 9. So I've got both a and b here. So this square, I just look above and to the left. It's a times a, which is a squared. The next one down, I look above, it's an a. Below, it's a b, so this is an a times b. And below that, I've got 3 times a, so I'll write that as 3a. In the top middle, I've got an a times a 3b, so I'm going to write that as 3ab. I'm going alphabetical on the variables. Doesn't matter, you can write 3ba if you want, but alphabetical helps my organization. Below that, I've got a 3b times a b, which is 3b squared. And below that, I've got 3b times 3, which is a 9b. And then over the upper right, I've got negative 9 times a, which is a negative 9a. Below that, I've got negative 9b. And then below that, I've got negative 3 times 9 is negative 27. All right, so there are some like terms to combine here. And if I do that, I end up with, let's see, the a times a would give me the a squared. And then I've got a positive AB and 3 more ABs, so that's 4 ABs. And then I've got a 3A and a negative 9A, so I'm going to call that negative 6A. Negative 9 and 3 is negative 6A. Then I've got a 3B squared. Then I've got this 9B and a negative 9B, which cancel completely, right? These cancel out completely. So the last thing I have here is a negative 27. All right, there it is. That's long, the two of them together. I promise you, I know that you're taking a test in 40 minutes. Your test will not be this long. The point here is for you to look at these problems, try them, and then check your answer. And if you're completely clueless about it, then watch that whole section in total. Don't watch this whole thing. Sitting and watching this or falling to sleep, this is not going to help you learn math, right? You're going to learn math when you're doing it and doing it independently and gaining confidence as you do it and you see you're doing things correctly. This is just here so that you have a chance to kind of start. You can see some insight into how you might begin. I will be sending out an email discussing some other ideas I have for studying for the test, but let's stop this right now. We're at 40 minutes and this is part 2. I'll talk to you later.